We're going to look at titrations, starting with a strong acid and a strong base. You're going to want to remember all of your strong acids and all of your strong bases so that you know how to do the problem when you have a strong acid and a strong base. The equivalence point is the point in a titration when the equivalence of acid equals the equivalence of base. So if we look at a titration curve, we typically would add base, and so this would be your starting point where you have 0 base, and then we would have the pH going up this way. So if you see that the pH is starting low, that means that you're adding base. So the pH will start low, your equivalence point would be right here at the midpoint. So pretty much the inflection point, somewhere around there. And then you would get to a plateau and your pH would stay constant. So your equivalence point would be at this midpoint. If instead you were adding acid and in your flask you had base, your pH would start high and then you would get your inflection point somewhere around here, maybe a little over, probably over a little more, and that would be your equivalence point. And then your plateau would be lower like this. So if you see a titration curve where your pH is starting low, that means you're adding base. If you see a titration curve that's starting high, that means you'd be adding acid. So let's do a typical problem where you have a strong acid and a strong base. So we have sodium hydroxide and we have hydrochloric acid reacting in a forward direction. And in this situation, we will need to calculate the moles. So we will take the volume of the base and convert it to liters, multiply it by the molarity of the base, and the liters would cancel. And so you would get an initial moles of the sodium hydroxide. You want to do the same with the strong acid. You convert the milliliters to liters, multiply by the molarity. The liters would cancel and you would get moles of your acid. So this is a limiting reagent situation. We subtract the moles of base because the base is a limiting reagent. So we subtract the 0.00100 moles from the base. So we get 0 base. The base was all used up. We subtract the 0.00100 moles from the HCl. The HCl is in excess. So we still have some moles of HCl, 0.00150 moles. Now the volume is additive. So we would take the 10 milliliters of base that we had added to the 25 milliliters of HCl. So if you add those up, then that's how you would get your 35 milliliters total volume. So that 35 milliliters total volume, you would convert to liters. You would put that as your volume, and then you would use the moles of acid over the total volume, and that's how you would get the molarity. So the final molarity is of our HCl. We calculate that. We get a molarity of the HCl. So this molarity is also the molarity of the hydrogen ion because HCl is a strong acid. So therefore, we just need the pH of the hydrogen ion, and we get the pH of the solution. So what you're going to want to do when you have a strong acid and a strong base is set up the equation. The first step will be to calculate the moles of the base, calculate the moles of the acid. Typically, one of them will be the limiting reagent. In this case, it was the base. And then you would have the moles of just your acid. Remember always that this volume is additive. So remember that when you're calculating this, this volume is going to be your total volume. So you're going to get your total volume by simply adding the volume of the base to the volume of the acid. Then once you get this, you just go ahead and solve this to get your molarity of your acid. And then we know that HCl is a strong acid. So whatever the molarity of the acid turns out to be, that is also the molarity of the H+. We'll do this one next time.